Jai Hind students. So in the previous lecture, we have discussed about the series clipper circuits. So clipper circuits are the circuits which are consisting of two components, that is diode and a resistance. And these clippers are categorized broadly into two categories, biased and unbiased clipper. Biased clippers are those clippers in which we have an additional battery, and unbiased clippers are those clippers in which we have only two components, that is the resistance and a diode. So again broadly we can say we can categorize the clipper circuits into two categories, that is the series clipper and the parallel clipper. Series clipper and parallel clipper both can be biased or unbiased. Also they can be the negative clipper or the positive clipper. So I can say that fundamentally we can say that the clippers are two types of the circuits, that is the series clipper and the parallel clipper. Series clipper can be biased and unbiased. Series clipper can be negative clipper or the positive clipper. So it can remove a portion of the positive signal or it can remove the portion of the negative signal. Similarly, I can say that the parallel clipper are also can be subdivided into the categories, that is the unbiased clipper or the biased clipper. So here we can see this is the first simplest parallel clipper circuit, which is unbiased clipper, because it in this case I can say that diode is connected in the parallel with the output. Also it is having only two components, so no additional battery is connected in the circuit, and that is the reason it is unbiased clipper. So let us see if it is your negative clipper or the positive clipper. That we can only say after doing the analysis. So let us start the analysis. Here you can see that during the positive half cycle, let me mark this terminal as the terminal A and this is terminal B. So for the first half cycle, your diode is at terminal A will be at positive potential and B will be at negative potential. So this positive will make your diode forward bias. So I can say that for the positive half cycle, diode is forward bias. That means it is on, or I can say short circuit. So if it is short circuit, then output will be equal to how much? It will be V0 will be equal to 0. Why? Because we know that this is your ideal diode and it will offer you 0 resistance when it is forward bias. So if it is resistance is 0, if we say that resistance is 0, then whatever current is flowing through it, the voltage across this load will be equal to 0. So if voltage across this load is 0, then output voltage will also be 0, because in parallel voltage is same. So that is the reason your output voltage will be equal to 0. That means for entire positive half cycle, your output will be equal to 0. This is your output waveform. Now coming to the negative half cycle, for negative half cycle, your terminal A will be at negative potential and B will be at positive. So we can see that this positive will make your diode reverse bias, because positive is connected to the cathode of the diode. So your diode will be off, that will be open. For this, diode will be reverse bias, that means it is open, or I can say my diode will be in off state. So if it is open, then I can see that what will be my output? That means this is not connected in the circuit. So what is my output? Output will be equal to input. So V naught will be equal to Vi. So I can say during the negative half cycle, my output will be equal to input signal. So here we can see that our positive half cycle clipped off. So that is why it is a positive clipper. So suppose if I change the orientation of the diode here, then if I change the orientation like this, so during the first half cycle, this terminal will be positive and this will be negative. So this will make your diode reverse bias. So this will be open. So if it is open, then output will be equal to input. And for the negative half cycle, this terminal will be at negative potential and this will be at positive, and this positive will make your diode forward bias. So diode will be forward bias, that means short. So output will be equal to 0. So if I draw the output waveform, so my output will be for this circuit. Output will be equal to input for the first half cycle and it is 0 for the negative half cycle. So under this I can see that this negative has been removed. So this is your negative clipper. So this is how we can do the analysis of the clipper circuit. So these two circuits are all we are talking about the unbiased parallel clipper circuit. So coming to the next circuit, that is a biased clipper circuit. Here why it is biased clipper circuit? Parallel biased clipper circuit rather. So here we can see it has two components and the diode is connected in series in parallel with the output, and also it has an additional battery in the circuit. That means it is a parallel biased clipper circuit. So let us start analysis of this circuit. So for the first half cycle, initially you can see that this battery, you can see this battery V volts this V volts making the diode reverse bias. Here you can see that this positive terminal of this battery is making your diode reverse bias, whereas this positive of the during the positive half cycle, this positive terminal will try to make diode forward bias, but this voltage will be able to make your diode forward bias only when your Vi is greater than this V volt. So here you can say that your transition voltage will be V volt. So let me draw the input waveform first. This is my input signal. Let's say this is Vi. Let me take this value as the 10 volt. This is minus 10 volt to understand the problem in a better way. And let me take this voltage as 2 volts. Fine. So I can say, and my diode is an ideal diode. So if your diode is ideal diode, then up to 2 volts, your diode will be in a reverse bias state. So I can say when my Vi is less than 2 volts, then diode will be off. This will make your diode reverse bias. So diode will be off, that means it will be open circuit, and if it is open, that means output will be equal to input. So I can say up to 2 volts. Up to 2 volts. My output will be equal to how much? It will be equal to input. So this will be my, I am drawing the output waveform in the input signal only with the green band. So output will be equal to input. So I'll get this output. Now as soon as my Vi is greater than 2 volts. Greater than 2 volts means during this time period. So my diode will be forward bias. So if it will be forward bias, what will be my output? If you look at this circuit, and if I write the KVL in this circuit, so I'll write 2 volts minus V naught is equal to 0. So V naught will be equal to 2 volts. It will be 2 volts. So during this time period, when your Vi is greater than 2 volts, then your output will be equal to 2 volts. So I'll get my output 2 volts. This. Again, coming to the next section, during this time period, again Vi is, so I can say 0 to T1 and T2 to T3. Vi is less than 2 volt, so diode will be off, so output will be equal to input. So this is your output. Now coming to the negative half cycle, T3 to T4. So during the time period T3 to T4, which is the negative half cycle. This terminal will be at negative potential and this will be at positive. So see, this negative will make your diode reverse bias. Also, this battery is also making your diode reverse bias. So throughout the negative half cycle, your diode is in off state. So diode is off. Off means open circuit, and if it is open circuit, then V naught will be equal to Vi. So this is your output waveform. So I can say the output waveform of this circuit will be like this, and this value will be equal to 2 volts, and this is 10 volts. So this is how we can solve any parallel circuit. Let us take one more problem. Here you can see the diode direction, and in the second problem, the orientation of the diode has been changed, and also it is connected to the negative terminal of the battery. Okay. So again, let us start the analysis. Now I take this diode as the silicon diode, and let us take this value as the 5 volt. Let us take this battery as the 5 volt, and I am taking the signal as 20 volts, and this is also 20 volts. So let us start our analysis. Initially, during the positive half cycle, this is your positive and this is your negative terminal. So we can see this positive will make your diode reverse bias, also this negative will make your diode reverse bias. So I can say that for entire positive half cycle, of Vi, your diode will be off. It will be reverse bias, that means it will be open circuit. So if it is open, that means output will be equal to input. So you can say 0 to T1, 0 to T1. V0 will be equal to Vi. So let me draw this. This is, let's say, small t1, this is t1. Now, coming to the negative half cycle. Negative half cycle, this is negative and this is positive. Now, the battery, the negative terminal of the battery will make your diode reverse biased only, but this negative terminal of the input will try to make your diode forward bias. But it will be only possible when the input voltage overcome this signal. So this is the value, it is minus of 5.7 volts. This 5 volt and this 0.7 of the barrier potential. So the net voltage, you can say the transition voltage. What is transition voltage? Transition voltage is the voltage when your diode changes its state. That means if it is on and it goes to the off state or off to on state. तो जब भी वो transit करेगा एक state से दूसरे state में, तो उस voltage को हम कहते हैं transition voltage. यानी उस voltage से I mean the above that voltage your diode may be in the on state, and after that voltage your diode will be in the off state. So that we will see here that the transition voltage in this particular example, your transition voltage is minus of 5.7 volts. So I'll draw the transition voltage, that is minus 5.7 volts. So up to that value your diode will remain in the reverse bias state, and after that it will be able to come in the forward bias state. So I can say that during the time period T1 to T2. So let's say this is your T2. So T1 to T2. Because your Vi is less than minus 5.7 volts, so diode is off. So again you get V0 is equal to Vi. That means this. And as soon as so this is T1 and I can see this. Now, as soon as T2 to T3, this is T3. So during time period T2 to T3. Vi is greater than minus of 5.7 volt. In this period, Vi is greater than minus 5.7 volts. So diode is on And when your diode is on, then the equivalent circuit will be minus plus VIE this is your, so if I write this is 0.7, this is 5, minus plus minus plus. So if I write KVL here, then it will be minus 5 minus 0.7 minus V naught is equal to 0. So V naught will be equal to minus 5.7 volts. So I can say that my output will be equal to minus 5.7 volts. Again, T3 to T4 during this time period. T3 to T4, again VI is less than 5.7 volts. So again your diode is in the off state. So V naught is equal to V. So this is your output waveform. So this is a biased negative clipper, because here in this case this portion has been clipped off or removed. So this is a biased parallel negative clipper. So this is how we can do the analysis of the various clipper circuits. So here you can see the various circuits. So let me take one more example. Let us take this example. Let me see the problem. Again, I am taking this as the silicon diode. I am taking this as let's say 4 volt. This is V naught. This is VI. And let me draw the input signal. Let me take this as 16 volts. I'm taking this as 16 volt. This is minus 16 volts. I've taken some numerical value to make this example more clear to you. So now starting with the analysis during the positive half cycle, you can see that the complete during the entire positive half cycle, that is 0 to T1. During 0 to T1, this terminal will be positive and this will be at negative potential. So this positive we can see making our diode forward bias, and also this negative will make our diode forward bias. So I can say that during entire positive half cycle my diode will be in a forward bias state. So I can say the diode is on. So if your diode is on, then the equivalent circuit will be plus minus VIE. This will be replaced by a barrier potential of 0.7 volt, because this is your silicon diode. So this will be 0.7 volts and minus plus, this is your 4 volts. This is plus minus V naught. So what will be my output voltage? In the second loop I have to write the KVL. So if we write the KVL, it will be minus 4 plus 0.7 minus V naught is equal to 0. So V naught will be equal to minus 3.3 volts, isn't it? it will be minus, because this is plus, minus, minus, plus. So, it is minus of 0.33 volts. So, if I draw the output waveform here, so I can say that my output will be equal to minus 3.3 volts. This is my V naught. Now, during the negative half cycle, this terminal will be negative and this will be positive. So, this negative now will try to make your diode reverse bias, but it will not be possible till the time this negative voltage will overcome the net potential of this. So, what will be my net value, after which my diode will be able to make your diode forward bias, that is your minus 4 and 0.7, that means minus of 3.3 volts. So, I can say this is my transition voltage, minus 3.3 volts. So, I can say that during the time period T1 to T2, during the time period T1 to T2, again my diode remains on. So, again my output will be equal to V naught is equal to 3.3 volts. So, up to T2 I will get the voltage, that is 3.3 volts. But as soon as I will come in the cycle when during T2 to T3, now during the time period T2 to T3, because my VI is now, my VI is greater than minus 3.3 volts. So, your diode will be off. Off means it will be open circuit. Open circuit means output will be equal to input. And what is my output? Input, input, this is my input. So, output will be equal to input. And again, during the time period T3 to T4, again your VI is less than minus 3.3 volts. So, diode will be in on state and output will be equal to 3.3 volts. So, this is my output waveform for this giving circuit. So, here we have discussed the various clipper circuits, series parallel clipper circuits. In the previous lecture, I have discussed about the series clipper circuits, biased and unbiased series clipper circuits. So, in both the cases, you have to take the each and every individual circuit and you have to analyze the circuit at every instant of time of the input voltage, because as the magnitude of the input voltage is changing, your condition of the diode will also be changing. And always remember, then while you are dealing with the clipper circuits, whether it is parallel clipper circuit or the series clipper circuit, the very important key point or the keyword is the transition voltage, because we have to identify, in every case we have to identify the transition voltage. And what is transition voltage? Transition voltage is the voltage where your diode transit from one state to the another state. It can transit from off to on state at this voltage, or it can transit from on to off state. So, if you clearly, or if you properly identify the transition voltage with the polarity, whether it is a positive voltage or it is a negative voltage, it makes your problem very simple. So, this is how you can do the analysis, and I'm sure this lecture will be fruitful for you. And if you come across any kind of problem, then I'm in the college itself, so you may come at any time to discuss the problem with me. So, thank you. Jai Hind.